Assalamu alaikum dear students. Today we are going to discuss few more example and this questions of this current exercise. That is how maximas and the minimas are used. That is derivatives are used in solid geometry. Now the first question is a square piece of tin with side 18 centimeter. That we have a square of with side 18 centimeter is to made into a box with out of by cutting a square from each corner and folding up the flaps to form a box. What should be the side of the square to be cut off so that the volume of the box is maximum? Now here this hole is square with side 18 centimeter. It has four corners, so we have to cut four squares from each corner. From the remaining portion we have we have to make a box in such a way that the volume of this box should be maximum. Now let the square cut from each corner is of length x centimeter. That is the side of the square is x centimeters. That is we have to cut a square with side x centimeter from each corner. Then we have to fold these four flaps. Hence we get a box without top. Clearly the length of this box is 18 minus 2x because from from adjacent corners we are cutting two squares of length of each having length equals to x centimeter. Breadth of this is again 18 minus 2x while as its height of the required box is x centimeter because when we fold this flap its height is x centimeter because we cut a square of length x centimeter from each corner. Hence the volume of the box is length into breadth into height, which is x into 18 minus 2x whole square. So this means that volume is the function of x. Now we have to find under what conditions the volume of this box is maximum. So we will use the second derivative test to check under what conditions this volume is maximum, that is at which values of x this volume is maximum. Now the first derivative, that is v dash of x, is this 12 into 9 minus x into 3 minus x. For critical points v dash of x is 0, which implies that x equals to 9 and x equals to 3. Now also v double dash of x equals to, because for in second derivative we need double derivative, that is v double dash is minus 24 into 6 minus x. Now at x equals to 9, v double dash is positive, which implies that when it is positive volume is minimum, which is not possible because we have to find the maximum volume. Now at x equals to 3, v double dash of x is negative, so this means that x equals to 3 is the local maxima, and the maximum value of this maximum value of the volume of the box is possible only when x equals to 3 centimeter. Hence in this way we have to cut a square of length of side 3 centimeter from each corner, so that after folding these flaps the volume of the box is maximum. Hence in this way we use the maxima and the minima, that is the derivative concept in this problem of solid geometry. Now the another question of this type is, of all the closed cans are simply but those cans which are right circular cylindrical cans with the volume of each can equals to 100 cubic centimeters, we have to find the dimensions at which the surface area of the can, that is the cylinder, is minimum. Let R and H be the radius and the height of this can, that is circular, this right circular cylinder, which implies that volume by definition is pi r square, H, that is 100. Hence H equals to 100 upon pi r square. We know that the surface area, closed surface area or total surface area of this right circular cylinder is 2 pi r into H plus R. Substituting this h as 100 upon pi r square, we simply get s equals to 2 pi r square plus 200 upon r. So this means that surface area is here function of r. So we have to find the condition at we have to find r and h such that this s is minimum, that is surface area is minimum. Here s is the function of r, h is the function of s in this r. So we will find the condition of this r at which this s is minimum. For this we will use the second derivative test. For critical point ds by dr is 0, that is r equals to 50 upon pi whole raised power 1 by 3, that is cube root of 50 upon pi. Now d2s upon dr square is 4 pi plus 400 upon r cube. Now this is the critical point. Now we will check the sign of this d2s upon dr square at r equals to cube root of 50 upon pi. Now it is positive when we substitute r equals to 50 upon pi whole raised power 1 by 3 in d2s upon dr square, it is positive. By second derivative test, s is minimum, surface area is minimum when r is 50 upon pi whole raised power 1 upon 3. So this means that this is one dimension at which the surface area is minimum. Similarly, we will find its height, that is substituting r equals to 50 upon pi whole raised power 1 by 3 in this h, in given h we get h. In this way we find the dimensions of the dimensions of this right circular can whose volume is 100 cubic centimeter and the surface area is minimum. Now the problem third is prove that the volume of the cone that can be inscribed in the sphere of a radius r, capital R, is 8 upon 27 of the volume of the sphere. Now if we have a circle and cone inscribed, if we have a sphere of radius r, inscribed cone in this sphere is that cone whose vertex and the end points of this diameter, that is diameter, lies completely on the boundary of this sphere. Let's assume that the radius of this sphere is capital R, while as the radius of this cone is small r and its height is h as shown in this fig. Then the volume of cone is 1 upon 3 pi r square h. Also h is from the vertex of cone to b, that is length of the point vertex up to b, that is this line segment to b up to vertex is h, which implies that h is equal to r plus ab. Now ab can be calculated in this triangle by using the Pythagoras theorem. Hence in nutshell we can simply say that h is equal to r plus root of r square minus r square, that is v equals to 1 upon 3 pi r square into r plus root of r square minus r square. Now its derivative with respect to r is this by using the product rule of differentiation, while as it is double derivative is this very quantity. You can easily calculate this very expression from the given dv by dr. Now for critical points, dv by dr is 0, which implies that r square, from when we put dv by dr equals to 0, r square equals to 8 by 9 capital R square. When r square is 8 by 9 r square, substituting r square in d2v by dr square, we get a d2v by dr square less than 0, that is it is negative. By second derivative test, volume of cone is maximum. Hence the maximum volume is obtained by putting r square in given v and putting h in terms of this r, which is 4 by 3 upon 4 by 3 into r. Hence v equals to 8 by 27 into 4 by 3 pi r cube. But we know that the volume of sphere whose radius is capital R is v equals to 4 by 3 pi into r cube. Hence v equals to 8 by 27 vs. This means that the maximum volume of the cone that can be inscribed in a given sphere, its volume is 8 by 27 times the volume of the sphere in which it is inscribed. So in this way we completed this whole topic about maxima and the minima, and inshallah in tomorrow's video lecture we will discuss about the approximations, how we find the approximations of a given quantity by using differentials, that is by using the concept of derivative. So thank you.